All right. I'm waiting for some people to show up, and then we'll get right into this. This is not actually an OBBG stream. I will not be doing any OBBG, and nothing of what I'm about to say is actually in the current OBBG code, although it could end up there someday. Can you hear me fine? Okay, so, excuse me. All right, so I don't have any code to show this in. I wasn't planning this, and I'm explaining all this because this will go in the archive still. So I don't have any code to show, so I'm just going to draw pictures with a mouse. So you have to bear with me, and if I had an easy demo app to do this in, I would actually just show it in code, some of it in code. But basic thing that you learn about making a game is that you have a main loop that so you have that's terrible. You have input. Oh, this is really slow. You have this loop that does input, simulate, and render. Right, that's your classic game loop, early game loop. Now, the whole discussion that I'm about to get into here was inspired by the fact that John Blow is talking about trying to do a frame rate independent braid in a smarter way to better handle really high frame rate monitors. And I have no experience trying to actually do that. So, the best way to do that, especially for a 2D game, like most of my sim knowledge is for more physics-y sim as opposed to the sort of hacky platformer sim that you tend to have. So I don't know exactly how this applies, but the concept that I'm going to present, I hope is helpful. Okay, so when you do this, what happens is your input, your sim, and your render all are processed at the same rate. And generally, we're okay with the render rate is kind of driven typically, by your performance or by your V-synced monitor or whatever, and is sort of out of our hands. And it's kind of what we think of as the main frame rate because it's the display frame rate. It's like the animation film frame rate. Input, I've never done it, but I know Quake or something like that actually would input multiple times per game frame just to make sure they didn't miss events. And I don't know if they actually tag them and how they fit that into the sim. But then in a typical game, a classic single-threaded game, the sim would run in between the input and renderer. And so if the renderer frame rate was inconsistent, the sim would have to handle an inconsistent frame rate. And there are multiple ways to do that. One classic one is to have your sim actually run at a fixed frame rate, say, 60 frames per second. And if this sim loop is running slower, you have the sim run multiple steps. And if you do that, you have this problem where you have like a half a frame of sim that you can't do any sim, and you have to wait around for the next frame, and that causes some staggering. And in the stuff I've done, we've actually done that, and it's never been a problem, but that's because we were never trying to do real high quality. But none of this matters. I just want to communicate some of the parameters and some of the limits of my knowledge, but the basic thing I'm going to talk about is viable. It's maybe overkill for a lot of platformers, but the way of thinking at least gives you, which I still haven't described, I'm sorry, we'll get there, at least gives you a way of thinking about the problem to know what an answer is that you can perhaps then use. So if I think about a timeline instead of a loop, So the thing is, what the computer is going to do is a loop of physical discrete statements, but you have to think past that. And so you have to think, okay, I have a timeline here. Here's 0 starting here, and time passes and stuff happens. So, maybe here's who knows, 100 milliseconds. And a way to think about it is that we have an evolving system that is continuous, not discrete. So this thing encourages you to think of each sim step as having discretely. And what I want to think about is that I have a world. So like, suppose I have an object moving, and so it moves on a straight line, and then it moves with a parabolic motion, and then it collides with something, and now it goes this way. And I'm only showing one axis, so you can't see the things it's colliding with. Those are potentially static things in this description. Okay. Suppose, so what I conceive of is I conceive that I have this totally independent, continuous system out there, and I have frames. And so a classic system, maybe the frames are falling here. Let me use a different color. Maybe the frames fall here in a classic system because the motion of the object can only change on frames. And so what people tend to think about a lot of the time is that they think of the state of the system here, and the state of the system here, and the state of the system here, and wherever the next tick is, and the state of the system here. That's supposed to be up, where that line would go. And they don't think about this as necessarily, these are means to an end. These are not the state of the system. These are just an artifact of what you're simulating in some sense. But what I like to do is think about, this is the state of the world, this continuous motion. And we're only ever going to sample it at discrete steps. And we're never going to know exactly what state the system was in, but we're simulating a system that does continuously evolve through these things. So the first thing that I handle, this is set to, the first thing that I handle a lot of the times in my engines is, suppose my frame rate was still fixed frame rate, but it was spaced out like this. Suppose like these were my frames. So I'm simulating a frame, and I have some linear motion of my object, but I detect that it's going to hit the ground or something that's very easy to determine. And it's going to hit the ground right here partway through the time step. In a lot of games, I might say, like, suppose I want bouncing motion. So let's actually draw a new graph. Suppose I actually want like this object that, say this is the x-axis, so it's bouncing off a wall. So it's just going to keep going, and then it hits another wall and does this. In a lot of game engines, or platformer games, I might be okay with the idea that, if here's the time steps, I might be okay with the motion that I simulate hits the ground here and doesn't move for the rest of the frame. And then the rest on the next frame, it moves back. And I don't really care about the inaccuracy of that. That happens a lot of the times when I'm coding a game or something. Did anyone else ever show up, by the way? Oh, okay, good. So in some circumstances, that's okay. So like, so I'm being really vague about this. So let me be concrete, I guess, and say what I'm doing here. So, oh, I just edited the wrong brush. Erase. Oh, it's because I'm in this mode. Let me be concrete about what I'm talking about. So I'm imagining a game where I say sim a single tick, and I do some math, and I say, okay, x plus equal, or yeah, let's say it's x plus equals dx times dt, and my end of my time step is here. And so what I compute is I've got the current position here. Whoops. Come on, can we get, oh, I switched that color again. I only get 2 colors in Photoshop, so terrible. So I have that data point here, and I compute this point here, because I say, oh, my current velocity times the time step, that puts me there. That's through the wall, so I move my position back, and what I actually compute are these 2 numbers. And I never compute that point, because on this axis, it's this coordinate, but I'm never, like, whatever point in space that would be. I might stop the y motion, or I'm just reflecting it. So this is like code that looks like, x plus equals dx times dt, or that should be vx, really. Right, so I'm computing how far I get to there, and then I say, you know, if x less than 0, and you'd be more likely to, you know, this is not how you'd actually do collision. Then I'd curly brace, and I'd say x equals 0, not how you do collision with real objects, but it's close enough. So I have to stop the motion, and then I reverse the velocity, right? So this is the kind of code I'm talking about here. Okay, it's all well and good. So hopefully that makes sense, right? This is saying move along here, snap back to this point, and reverse. So, you know, this graph is a graph of x versus t. Okay, so in some games that's acceptable. But what I'm talking about now is this frame rate independent idea, or there are other reasons you might have this. Where you want that motion to be more accurate and, you know, floating point precision accurate or whatever. So you really want, let's see, I had it stop there. You really want it to bounce there and be more accurate, and then it might bounce again here. So how do I implement that when I'm implementing something like that? So then the time step is here. Okay. Let's just make our t-graphs pink. So what, because I'm only going to compute, in some sense, a position here and a position here. It would have been here to there, but now I have to compute it as being here and traveling in that direction. So yeah, that was a 0, not the point. Right, so somehow I have to compute that position and that velocity. And as I was saying in the Twitter discussion, the way I actually do that is by running this code. Running this block of code twice. I run it from here to here, and I run it from here to here. And the way I do that is by having that all in an if statement, and this dt is now, you know, say the function is, you know, sim, and it takes a parameter dt was how I had written this before. Now, instead of sim taking a parameter dt, it takes a parameter, you know, say this sim is a fixed time step. It can work with either. So say it takes a fixed dt. Then what does this code look like? This function, instead of being our sim function, is our sub step dt. And our main function says t equals collision time. Starting at x, moving at vx for fixed dt time. So this thing has to internally compute the path and find the collision. So it's going to compute that thing. And it's going to compute how far along here it goes to reach that point of time. And then this is going to say, you know, execute that substep. So we substep from 0 to t, from, in this case, from 0 to t. And then we fix dt. We've consumed some of our fixed dt. We've consumed t of it. Minus equals t. I should have called that dt as well, but whatever. And then we actually put this in a loop. which is a loop of while fixed dt is greater than 0. So what ends up happening computationally is we compute that point, we compute that point, and we compute that point. When we return from the function, we'll just have that point and we'll have that point. But we're going to go ahead and think about all of the steps that happen within. It can be multiple steps. So if you go back to this and you pick a variable time step, you know, so let me do this real quick. So if my time steps are here, for the first time step, I go, okay, there are no collisions in the entire time step, so I substep it all the way, and I end up here. And then for the second time step, I see the collision here, and I substep up to here. And then for here, I see that there's a parabolic arc, so I do the math for a parabola and compute exactly this point. I don't like follow the straight line motion. I actually compute the parabola, which is just an extra term in the thing. It just means instead of computing, you know, y plus equals, let me do this on a different layer, on the main layer. Instead of computing y plus equals vy times dt, I compute y plus equals vy times dt plus or minus, depending on your terminology, gravity over 2 times dt squared. A very important thing is that because this is a discrete simulation, at some point you update your vy. So to do this simulation correctly, don't update the vy until after you compute that. And now you say vy plus equals g times dt. And within float precision, this will always produce the exact same parabola, even with different things. Okay, so that was why I was saying about this. We computed along this parabola. Then for this time step, we continue along the parabola, we detect that, etc. However, you know, if your time step were long, so if your time steps were here and here, then you would find the first collision, do that. You would compute parabolic motion and somehow detect a collision along parabolic motion, which I admit is not something I normally try to do correctly, and would be inconsistent if you don't do it correctly. You would detect that point, and then to finish off the time step, you would end up at that point. So I'm pointing out there is an issue here with this thing. The point of this is not that this is a perfect solution. The point of it is to think of the model has nothing to do with where the time steps fall, right? The time steps are how you decide what to output from the sim, but the model is that time is always happening continuously in between the time steps, and you're just trying to treat that. Now, I might as well mention some little other side issues, and nobody has any comments yet. So one issue you have is that typically in a classic platformer sim or whatever, you'll stimulate each object separately for each frame. This is the part where I don't know what the right way of dealing with for like a braid style platformer, what the right way of making it frame rate independent really is. I don't know what the tricks would be. So the two issues are that you're not doing a real physics sim. So a real classic physics sim, I think we did it this way for Thief. We had a variable time step because we just ran the sim once between frames, and we had a continuous collision detector, although it did treat things as straight lines instead of along parabolic paths. So we could determine exactly where things collided. And rather than simulate each object independently, we simulated all of time forward. So we wanted all things to progress like they really would. And the way that the classic way to do that is you look at all the objects and you find the time of their first collision, like we were talking about here with this time of first collision. But you find the time of first collision for all objects without doing any more simulation of them. You don't advance any of them. Once you find the time of simulation for collision for all objects, you take the lowest one and you simulate all objects up to that point. Because up to that point, nothing else can happen. When you get to that point, those two objects that collided at that time, or more if they happen to fall at exactly the same time, can be processed. Their collision responses can be computed. And now they have new trajectories. And now you start sweeping the whole sim forward by, once again, going all over objects and checking when all of their collisions are. That can be very expensive, especially if you have to compare every pair of objects. But you still have all the old collision times from the original thing. So say you had 100 objects and 2 of them collide at this point. You can now just take those 2 objects and say, when do those 2 objects collide with anything else, including the other objects? And you can't miss anything because all the other objects, if they interact with each other, they're not affected by these 2 objects until these objects collide with another object. If any of that doesn't make sense, let me know. The fixed DT is larger than the fixed DT is, I'm saying it's fixed. It doesn't have to be fixed. This could be the per frame DT. You can run this function once per frame for each object, and so use a fixed DT, which is your actual game time. However, that's ignoring the problem of collisions and ignoring this problem I've just been talking about doing things in order. So I was just saying, this is the real way to solve it, is this sweeping time forward model where you make sure you've solved all objects. When you, at that point, you make sure you've processed all objects up to that point. Things like round corners, I haven't even tried, I don't know. So I just wanted to wave my hands at that classic solution. Again, a lot of this stuff is like 10 or 20 years old. It's just some people don't, maybe are not aware of this way of thinking about the problem, which I think is a useful tool, even if you're doing crappy, you do this crappy one where it stops like this. Being aware of what the continuous solution looks like makes you aware of what the errors that you're getting from this system are. Because OBBG does this kind of system right now. It doesn't even have bouncing though. But okay, and then so that's the object simultaneity problem. And I don't know of a good way to solve that problem if your goal is frame rate independence. The context I've almost always used this system is with a fixed time step, like I just have a 60 hertz time step. And if you only have a 60 hertz time step, you might wonder what the point of this kind of stuff is. Well, there's things like, trying to think of a good example. So one of the things is that if everything that can happen gets quantized to frames and you have a fixed time step, it's usually going to be pretty consistent without doing stuff like this. The kinds of things you run into are like, you throw a ball at a wall and it bounces off. So here's an example that you wouldn't necessarily run into. Imagine you throw a ball against a wall and it bounces off. If it bounced off different distances, that would be a problem. And this kind of system can have that artifact potentially, but it's actually unlikely to, because you're throwing the ball tends to be quantized to the frame boundaries. So there's no way for the ball to actually behave differently. As long as it is quantized to the frame boundaries. But if you can ever get this kind of thing to happen, and I'm sure it can happen, and I just can't think offhand of ways that can happen, you can definitely get artifacts where things do not consistently, even with a fixed time step, things do not behave exactly consistently. But it's less about consistency when you have a fixed time step and more just about sort of a quality and not consistency of that sense. Consistency of, you know that your simulation is closely approximating a real world system, so it's unlikely to have artifacts. I have a tablet, I just don't even have it set up. So, and I just needed to do this stream real quick, so I didn't want to spend time setting it up. I actually have a Cintiq and I have just a little tablet, but I don't have it out, so. let's see, what else is there? Okay, yeah. So then the other thing that you run into, and I don't know how you solve in the brain problem, which is the thing I think about a lot, which is why I went to fixed time step. The whole thing of having fixed time step loop, the way of implementing a variable time step. So here, the thing is that this gives you, with parabolas, this actually gives you a good solution for dealing with a variable frame rate. And this is something we dealt with a lot when we had software rendering and we were running, on a wide variety of PCs back in the 90s. So it was pretty much standard to just use a variable time step. Every frame was just not totally uncorrelated, but very different, potentially very different from the previous frame. And not to do it this way with a fixed time step, we would just do these, parabolas. And, I think, so what Thief did is, I think it did that sweep thing that I was talking about, but it meant that if your frame rates were different, if you had a much lower frame rate, the parabolic arc would be, approximated with a linear sweep for the collision detection. And so you could potentially get in a situation where, maybe a swinging door, it's probably not the best case, but a swinging door maybe could, collide with something or not collide with something depending on the frame rate, which just sounds like tunneling, but it's, I'm trying to think of a parabolic path, and that's not a parabolic path. So yeah, just picture, a fixed gun emplacement, which you didn't have in Thief, could potentially hit hit the ceiling or not hit the ceiling depending on the frame rate, which would be pretty bad. So thinking about things like that is what drove me to using the fixed time step, because then at least it'll be consistent. And the other thing, though, that drives that is a lot of the times you have sort of a game sim. You have this continuous sim with these sort of discrete moments of collisions and discrete impulses that you add to things. But you also have, whatever your game logic is somebody standing on this platform? Did they cross this line def? And those things you're generally only going to run once a frame, especially on a large team. When you have game programmers, you're not going to expect them to think about this sort of complicated continuous time simulation stuff. And if that logic is just going to run in this sort of discrete sampling the world way, the only way to make that make sense is to run that on discrete frames and consistent, fixed frames. And they can even run less often. You could have this physics sim stepping, at 120 FPS, and your game frames only sampling every 30 FPS. If that's enough for the quality you want, you'd run into some sort of inconsistencies there where, you could move on and off something in 4 physics frames and not ever detect it with the game frame. But that's just a general sampling problem that has nothing to do with, not very little to do with this issue. So, and like there's all sorts of variations like that with like having AIs only tick every once a second or whatever. You can see as sort of a variation on that because the AI is part of the sim in some sense. So I think the fixed time step thing has been an adequate solution, and I'm curious to see what John is thinking about for all this kind of stuff, trying to go back to a fully variable time step. But you can see that you can apply this method with variable time steps. There's nothing about the algorithm that requires fixed DT to actually be fixed. That's just sort of the environment in which I thought about it and wanted to use a different name than the DT that I was already using. So I think I've covered everything I want to cover. So Varia, however your name is pronounced, if you have follow-on questions, let me know. And if anyone else has questions, let me know. It's quite possible none of this was very clear. I'm not a Handmade Hero presenter expert, so. Resaying the initial problem statement was a very hand-wavy initial problem statement. The initial problem statement was some discussion on Twitter that suggested the person I was talking to didn't have this view of continuous time and was thinking only of the sort of discrete time, and that may be overstating what they were thinking about, but I wanted to make very explicit this notion of that you're imagining a continuous time and seeing samples of it, not that the samples are the actual state, right? The samples are samples of the state, not the state in and of itself. And the reason for that was because the whole problem of parabolic arcs when doing frame rate independent physics is what's the trigger for this. That you can easily write this parabolic code, and I always do, but you don't have to, because if you're running at a high enough frame rate and you just do the update the VY like this, you'll get a seeming parabolic arc. It's just a little off, and as long as it's a fixed time step, it'll be consistently off. And if you're consistently off, you don't care, right? So that's why you can get away with it if you don't care about all this stuff. But as soon as you want to think about the variable time steps, or the variable sub time steps, I think it's worth doing this so that you just know it's rock solid and consistent. Yeah, the classical thing that I was talking about was really just there was one specific paper. There was this whole era in the 90s when the graphics people basically started rediscovering, you had Baraf and I can't remember the other guy, the Impulse guy, basically rediscovering all the classic stuff. And one or the other of them, I think the Impulse guy, characterized that solution of the sweeping time and finding the first pair of collisions. Murtic, yeah. So it might have been Murtic. And the point is, we did actually, I believe, do that in Thief. So, hey. I'll let somebody in chat answer the question about what famous engines do. The game devs don't think of jumps as a parabolic arc, but a combination of motion and gravity. I just don't even know what you mean by that. Which is part of the reason why we had this whole thing, is because I don't really know what you meant, so I just figured I'd be very clear about what I meant. Collisions and rollback. Collision. Which only this behavior of standard time warp events. Okay, so yeah, I think that is exactly what I was thinking of. So yeah, maybe nobody else ever did it. Certainly by classic, I did not mean what anybody did in modern game engines. By classic, I meant back in the day. Yeah, here, this is exactly the thing. That was exactly what I was referring to. I don't know if you guys can see that on that scale. So to be clear, like if so the way I don't know exactly how people normally implement the jumping physics, where depending on how long you hold down jump button, you get different duration jumps. But I assume that the basic idea is, you know, that they add a jump impulse. And maybe they keep adding the jump impulse every frame while you hold it down. They maybe add a different impulse each frame to get different exact curves. I think that's what I tried once. And that's assuming a fixed DT, right? That only works when this is running at a fixed time step because you're adding an impulse. And if you looked at that graphically and asked what are we simulating in the system, it's a little ambiguous. You know, we have, oh, I'm still on the layer. Actually, that's good that I'm on the layer, because now I can erase. I don't need it white in my palette. So if you think about what that looks like graphically, so, you know, you're off the ground, so you're going to follow a parabola, right? So you, from that starting impulse, right? You were moving like that, now you start moving like that. So you would follow this parabola. Oops, that did not erase. Am I on the wrong channel again? I'm on the wrong channel, or layer again. And I can't erase that now because I did it on the wrong thing. What? No. There we go. That's the button I need to hit. Okay. Photoshop, every version of Photoshop I've ever used has the same stupid bug, which is if you change layers, draw, and then undo, it unchanges the layers. And so then you end up drawing on the wrong layer. Okay, so so here are our time steps. So this is what the parabola would be if you don't do anything else. So am I on the wrong channel? Or the wrong layer? Oh, this whole thing is on the wrong layer. And I can't draw white. So then here, if we add the impulse again, now we'll follow that arc. And then here we add that impulse again, and we follow that arc. And then maybe we stop adding it. And now we follow an arc back down, and it's not symmetric left and right. The arc is not the same shape. Of course, if our time steps were different or the impulse were different, the shape would change. So if you want to think about a way to do this that's time step invariant, I mean, it doesn't exactly make sense because you have you're saying that the jump velocity depends on how long you're holding down the button. So either you quantize, if you don't quantize how long you're holding the button down, you're going to get different jump rates at different frame rates. So let's just assume that's okay, that we're going to get different jump rates. Then obviously what we can do is like add a different jump impulse depending what our time step is to try to get the same shape. And you'd go, well, okay, how do I do that? What jump impulse do I need to add at each one? And that's a hard problem. And so we will sidestep it by instead looking at this from a continuous perspective. I guess I should leave this and draw a new one. So if we look at this from the continuous perspective, we don't even need these pink dots because we're not going to worry about where the time steps fall. We're just going to say that you're going to have to tune this, and you may a single value may not work. We're going to say, let's label this impulse brush. So this is impulse based. We're going to add a jump force, which stays sustained through time. And that's equivalent to changing the value of gravity while you're jumping. Right? So suppose we had tuned this so that this looked good for us. We were happy with this. And the fixed DT was 1/60th. right, when we did this. And then we're like, okay, we want the same jump shapes, but we want to do it with continuous forces. So what can we do? Well, we want to add the equivalent of that force. We want to add something so that if we add that force constantly at every point in time, we get the same effect as that impulse. And how do we do that? Well, we can back solve for what impulse will produce that effect. Remember, we said that g over 2 times dt squared has that effect on y. So what effect does that have on y? Well, if we're just doing the dumb physics, we're going to add the jump to our vy, and then the next frame or this frame, we're going to multiply that by dt and add that to y. So the effect of this was to compute y plus equal jump times dt every dt, every frame. So if we want to compute the equivalent effect using g over 2 times dt, then we want to say it has to add g over 2, well, not g, right, force over 2. It's not really a force, or it's, what's the word for the, it's an acceleration. That's a really hard word to remember. He said sarcastically. Times dt squared. We want those two to be equivalent, right? So we solve for them being equivalent, and we get the jump equals, or no, we want to solve for a. My bad. We get the a equals 2 times what? Jump over dt, is that right? And now our formula, our computation, where we were computing that, can look like this. Let's do it by overriding gravity effectively, right? So well, let's just say our total acceleration, this is the y acceleration, is gravity plus 2 jump. And we said we had tuned this so it worked at the frame rate of 1/60th, but that's no longer our frame rate. We're not going to assume that. So this is 2 times jump over 1/60th. So if we set the acceleration of that for a whole frame, we'll get the same effect even if our frames are different. But obviously, so here's our timeline. So now we'll follow some different parabola, which will hit the same sample points. Oh, and we still also have, don't forget, we have to actually update y velocity in the same way, right, with that new acceleration. So this will determine some shallower thing, and then at the time that we let go of it, we'll switch to the regular parabola and come back down. Something like that. It's over 1/60th, so it becomes 120 times jump. Some games set y velocity to 0 when the jump item is released. And so the point is you can still do all those kinds of things. You can even still do it as staggered impulses, because remember, I have this whole model of splitting things into the subtime steps. So if we wanted, we could say you're running at a frame rate where your time steps are this, and you want to add impulses at exactly these moments. You can actually still do that, right? You run this with a sub time step here, and then run to there, and that's your thing, and you'll find yourself there. And then you run the multiple sub time steps to there. So you can still do all that. But anyway, so whatever change you make, eventually they release the button. And that's presumably happening quantized to your frame rate. But if not, if somehow you can detect that they let go of the button there, you can do that. Then you can still just follow this different arc. Suppose your jump calibration doesn't work to add a fixed amount every frame. Suppose you found that adding a certain impulse on the first frame and a different impulse on the second frame and a different impulse on the third frame is the what you had to do to tune your jump to look good. Then again, treat it as continuous time that's following these arcs, and split it into these substeps like I was talking about. You can do that. So that's how I would tackle the jumping problem under this model of still trying to think of everything as continuous time. Okay, that's everything I wanted to talk about. So more questions, and then I'll stop, since this has gone way longer than I meant to. Yeah, you only have to roll back the relevant groups, not the whole sim, is sort of what I was waving my hands at about the, you find the new collisions for the objects you just updated, but you don't have to find the new collisions, any new collisions for all the old objects. But yeah, I mean, there's smarter, subtler things you can do with that. Right, so notice the moment you use terminology like changing gravity, you're thinking of it from sort of a hacky model. It's a model that works, and if that's the best way for you to think about it, you can think about it that way. But I don't think of it that way. I think of it as there's a constant downward force of gravity on the player as they jump, and there's the the hover craft that they're riding on that's spewing air downwards, that's pushing them up. That's another force that's being added on, and the final accumulation is the sum of those two. The gravity always applies when you're in free fall and never applies when you're in contact with the ground. In a true physics sim, you can simulate that by always having gravity applying to you when you're down on the ground, because you need that so that like you roll over, a misshapen object is pulled over by gravity. But for the physics, to the platformer physics, you can just think of it, gravity turns off when you're on the ground, and this is a force that's only on when you're holding down the jump button. No, I do not have any thoughts on all the problems that John Blow has talked about, because I haven't tackled any of this kind of stuff. Only thing I've implemented recently is 60 frames per second fixed time step stuff. They do not share their slope at the point in time when you change. Yeah, they share their slope. If you use impulses, they don't share the slope, right? Impulse is a discontinuous change in the first derivative velocity, so they don't change it. Changing the force of gravity is a discontinuous change in the second derivative. So changing the forces, I mean, not the force of gravity, but yes, changing the force of gravity as well. The 3. What is the 3? Oh, the theme. How can you adjust the theme to not have gradient title bars? Well, I use Windows 7, and somewhere in the personalize you can find that stuff. I don't actually want to try to dig into it, but you go into the personalize and you go to the theme, and then there's a thing that lets you configure each individual thing, and you can find the title bars, and the title bars have 2 colors, and there's 2. There's one for inactive and there's one for active, and you change the second color to be the same as the first color. And the colors you need are in the palette, the little palette that it gives you. You don't have to make a custom color. Yeah, this is Windows 7 though. You can still do it in Windows 7. I don't know about 8 and 10. But you can see. Constant color. And if I make it inactive, constant color. And I do that. Every time I install a new OS, a new Windows OS, I go in and do that. All right. If nobody has any more questions, I will end the stream. So I'll wait the full round trip here for follow-up. And I'll answer dumb questions after the stream in the chat. Not dumb. I'm not trying to insult your questions, sorry. But, you know, tangential questions. So, yeah, this was not a talk for people like Pear. I just wanted to get it in and get out quick, and so I didn't really explain it in the announcement. It was more aimed at the Handmade Hero crowd. So I'm glad I told you that after it was all over. All right, there are no more questions, so I'm going to shut down the stream. Thanks for watching. Bye-bye.